Hello, welcome to the talk Bringing Scale and Transparency to Proteomics Application with Serverless Computing, presented at 6th International Workshop on Serverless Computing. This paper was written by Gilbert Nick, Pedro Garcia Lopez, and me, Mariano Mirabelli. This work was carried out in the context of the Cloud Button project, which is a project funded by the European Union where URV Cloud Computing Lab engineers and researchers work in collaboration with IBM IFA. The motivation to this paper was to demonstrate that it's possible to move a proteomic WoSC application to serverless. This means that we can implement this application without requiring a pre-configured cluster of virtual machines. Additionally, we want to demonstrate that serverless enables proteomics application to scale transparently, which means they can scale dynamically without requiring any additional configuration. Finally, we want to prove how with serverless it is possible to improve the performance of proteomics application at the same time that we can maintain a cost comparable with the implementation of WoSC on virtual machines. Scaling transparency means that application can expand in scale without changes to the system structure of the application algorithms. Due to serverless computing support autoscaling inherently and proteomics applications must deal with high concurrency requirements, these kinds of applications can considerable benefit from serverless and scaling transparency. We take the WoSC framework and the replica exchange algorithm as a starting point for this work. The WoSC framework is a flexible master worker framework for building large-scale applications with the ability to run on cluster grids and clouds. On the other hand, replica exchange is a hybrid method that combines molecular dynamic simulation with the Monte Carlo algorithm. In this type of simulation, several replicas of the system with similar potential energies are generated in parallel with different temperatures over several Monte Carlo steps. Additionally, to implement the replica exchange, specific software packages that implement molecular dynamic mechanisms are required. In this work, we use Proteomic. The replica exchange architecture developed with WoSC is composed of a master process, a queue, and a set of workers subscribed to the queue. On the other hand, an execution of the replica exchange algorithm will define a series of Monte Carlo steps involving a series of replicas for each. This means that replica exchange will execute n by n molecular dynamic simulations where n represent the steps and n represent the replicas. As the molecular dynamic execution for each replica are independent among them, it is possible to run in parallel all the replicas that belong to a specific step. Therefore, for each replica, a task will be submitted to the queue in order to be processed by one of the workers available in the cluster. Additionally, replica exchange embeds Protomol calls to simulate molecular dynamics. Each call to Protomol requires an input file that allows it to work correctly. Due to the algorithm execute n by n calls to Protomol, the same number of configuration files will be required. In WoSC implementation, these files, as well as the result of each submitted task, are exchanged in direct communication between master and workers. On the other hand, we propose the following serverless architecture with disaggregated storage. In this architecture, only one VM is needed to implement the main program responsible for running the Monte Carlo simulation. Additionally, another VM may be required depending on the storage selected. Thus, for each replica in each Monte Carlo step, a new serverless function will be launched to execute it. Specifically, in our architecture, all replicas belonging to each Monte Carlo step will be launched in parallel. On the other hand, this architecture does not support direct communication and processes as WoSC does. Therefore, we require an external storage to save the required file that Protomol requires to work properly. As a consequence of this, at the beginning of the Monte Carlo simulation, the main program will upload these files in the storage, and then each serverless function will read this corresponding file in order to complete the assigned task successfully. To implement this architecture, we developed two serverless prototypes, one of them using IBM Cloud Offset Storage and the other using Redis. Also, both prototypes were developed with the LibHop framework. This framework provides an extensible backend architecture for compute and storage that is designed to work with different cloud providers and on-premise backends. For both prototypes, we use storage to hold the Protomol file needed to run the simulation. The decision to develop two alternatives arises from the idea of analyzing how this architectural decision impacts scalability, cost, and performance of the application. To demonstrate that serverless prototype meet our goals, we decided to run the following experiment. For each replica exchange implementation, we execute a set of algorithm repetitions varying the number of replicas in each one. Therefore, we took 12 replicas as our starting point, and we added 12 replicas for each repetition until we reached the 192 replicas. Additionally, we defined a 100 step of Monte Carlo as a constant. In terms of execution environment, this experiment was executed over the IBM cloud environment, mounting a cluster of 12 servers for WoSC implementation and configuring a function namespace for serverless prototype. Due to each worker of WoSC requiring one vCPU to work properly, we configured our function with 2 GB of memory to guarantee one vCPU per function executed. In this way, we set the same CPU condition on both architectures. As we can observe, after executing the experiment, the working implementation is slowest in comparison with the leapfrog prototypes. The reason behind this behavior arises from the communication and data transfer overhead between the master and workers that occur in WorkQ. This happens because each task triggered by the master needs to upload the corresponding file to the nodes to make it available for them. In addition, the output files are pushed back from the nodes to the master when a task finalizes its execution. Thus, according to the fact that the number of replicas increased, the number of tasks triggered increased too, and it generates an increment in the file exchanges, producing the growth in the total execution time of the simulation. Additionally, analyzing all prototype results, we can observe that the cloud offset storage prototype is slowest in comparison with Redis prototype. The reason is that offset storage is not designed for numerous read-write operations over small files. Also, offset storage is on disk-based storage, which is considerably slower than in-memory-based storage such as Redis. In the second plot, we can observe that cloud offset storage prototype is the most expensive. And this happens because the average function execution time of cloud offset storage prototype is higher than Redis prototype. Average function execution time has a large influence on the AVN cloud function pricing schema, which is calculated per second of execution per gigabyte of allocated memory. This means that cloud shared storage prototype is more expensive than Redis because cloud shared storage prototype is slower than it, but not as a consequence of the operations against the bucket. On the other hand, we observe that Redis prototypes hold the lowest total cost in terms of function execution. Thus, despite this prototype having an extra cost related with the requirement to configure an extra virtual server to host the database, it maintains the cheaper total cost by holding the function's lower average execution time. Additionally, we can observe in this table the total cost of mounting a cluster of 12 nodes of WorkQ implementation. In terms of scalability, we can figure out that serverless prototype scale transparently, but WorkQ implementation does not. In WorkQ, the number of parallel tasks supported by an application is measured by the number of workers available in the cluster. At the same time, each worker must be explicitly started by the application user, requiring a vCPU core to function properly. Therefore, it means that if we want to increase the parallelism degree supported by the application, we will require to start new workers, which could also mean providing more hardware resources to increment the number of vCPU cores available in the cluster. That was exactly what happened in our experiment. With the growth of the number of replicas configured in the replica exchange throughout the iteration of the experiment, it was mandatory to admit more virtual servers to satisfy the number of vCPU cores required to execute the count of workers needed. On the other hand, we observe that serverless prototypes scale transparently according to the application load. With our prototypes, when the number of replicas grow, the number of function invokers grow dynamically without providing extra configuration or hardware. In this code block, we can see how this feature is implemented throughout the map method of LeadHop executor object. This method receives two parameters. One of them is the function to be executed as a serverless function, and the other is a list data structure. This list has two purposes: to define how many functions will be launched in parallel based on the size of the list, and to define the input value for each function throughout the entries in the list. Therefore, in our prototypes, the data corresponding to all replicas for each step will be saved in a list that will be passed as parameter to the map function. As a consequence, the serverless implementation will dynamically adjust the number of functions that start for each Monte Carlo step based on the size of this list. In addition to scaling transparency, we also observe that LeadHop provides access transparency to all prototypes. This means that all prototypes are enabled to manage cloud resources as local resources through our well-known Python APIs. So if we look at this code block, we can see how, for example, serverless functions are managed with Python multiprocessing API. As we have observed, serverless prototypes reduce the total execution time of the replica chain by around 30%, avoiding the direct communication between master and workers occurred at WorkQ. Also, serverless prototypes scale transparently as we observed in the experiment, regardless of the number of replicas configured in replica exchange. And finally, serverless solution can obtain a comparable or even cheaper cost than a WorkQ solution over virtual machines, but this will depend on the average execution time of the functions. Thanks for your attention, and if you are interested in this article, I leave the link here along with the link to the source code of the serverless prototype. And if you have any questions, feel free to reach out to any of the authors.